Alright, this lesson we're going to look at nuclear decay. So we're going to look at three different types, alpha, beta, and gamma. But before we get to that, we'll kind of look a little bit at the history and what each of them are. First of all, Henry Becquerel, a French guy, was sort of the first to discover that uranium did some weird things. Basically what he found out was when it was in a closed drawer, and he happened to have some photographic plate in there, which is like film for old cameras. He found out that the uranium caused the plate to get exposed, and it made sort of a weird picture. So he assumed that the uranium was giving off some sort of radiation, kind of like visible light, and he was even able to show that a magnetic field could change the direction of that radiation. Shortly after, Marie and Pierre Curie, they were doing some experiments with radioactive elements like polonium and radium, and they found out that they emitted radiation no matter what, and they were the first to sort of describe the idea that they figured that radiation was coming from the core of the atom, the nucleus. And Marie Curie ended up being more famous later on for dying due to radioactive exposure and cancers and things like that. So now we know that basically what's happening is any kind of radioactive decay is coming from an unstable nucleus. So the nucleus is not stable. It wants to sort of rearrange itself and change to try to get more stable. So that's what happens when we have a decay process. If one element changes, so let's suppose we had an element like carbon and it changes some like oxygen or whatever, then we'd call that a transmutation if it goes from one type of element to another. So Rutherford was the guy that came up with three different types, and he found that it sort of depended on how big they were, how powerful they were, what direction they went, and so on. So we'll go through each of the three types. The first is alpha radiation. He found out that it was pretty minimal, and we already know, we've looked at alpha already, we know that it was the same as a plus 2 elementary charge, and he found that it was positive because in a magnetic field it deflected to the left. So if you look at this diagram at the bottom, if you put your thumb upwards, your B finger into the page, you can see your alpha particle then should go to the left if you're using your right hand. So it has to be a positive if it goes left, and he found that it was pretty weak. It could go through about one piece of paper, and that's about it. Beta radiation he found was a little bit stronger, and it was negative, and it goes to the right, and it can go through like a thin sheet of aluminum. And then gamma radiation he found out that basically was super strong. It could blast through lead, and it could not be deflected. So alpha, we'll start with alpha. So alpha particles, remember we've been talking about these pretty much most of the year, and really we know that alpha particle is pretty much a helium nucleus. So we know that if it has 2 protons and 2 neutrons, it would be a helium-4. So what happens is, whatever the chemical is, when it gives off an alpha particle, what it's doing is it's ejecting the 2 protons and neutrons out of the original nucleus, which often will make it more stable, or it might even have to do this 2 or 3 times to get it more stable, but basically it's getting rid of this alpha particle or helium nucleus. We don't call it helium because there are no electrons, and it's not just natural helium. It's sort of a byproduct of the nuclear decay. So we know it's positive 2 charge, and we know then if the chemical is going to lose two protons and 2 neutrons, then likely the chemical is going to change, and we can just basically do similar to what a chemistry equation would look like, and all we have to do is balance the numbers. So let's look at this example. So we have 16877 iridium. So 77 is the atomic number of iridium, and if we have 168, so we know that if we take out an alpha particle, we basically just subtract the 2. So if we subtract 2, we know it's a 75 element, which is Re. And if you look on your periodic table, 75 is Re, and that is rhenium. I'm not sure how to pronounce it, doesn't really matter. And if we subtract 168 minus 4, that gives us 164. So they have to balance out. So you basically just have to make sure your total protons, total nucleons total up, and we call that the conservation of nucleons. So the total numbers always match. So you can see we started with iridium, so that was our parent nucleus, or our original amount. We take out the alpha particle, and we're left over with a daughter nucleus, which was the 16475 iridium. So during this process, if we took the total mass of the daughter nucleus plus the total mass of the alpha particle, we actually get less mass than what we started with. And the reason for that is, to do that reaction, we had to convert some of the mass to energy. So we talked about this in the last topic, where we get a mass defect. So every time it undergoes a reaction, it's going to lose a little bit of mass because that mass was used up as energy to do the conversion. And we can actually still follow conservation momentum, all those kind of things, all those rules still apply. So let's do another one. Let's do uranium-238. So that means we have 238 uranium. And if we look on the periodic table, uranium is 92. So we know that it's going to give off an alpha particle, so that would be our 4,2 helium. And then we know the rest of it is going to be the difference. So 238 minus 4 would be 234. 92 minus 2 is 90. So we know then it changes to thorium. So we'd have 234, 90 thorium. And that's it. So alpha decay, pretty simple. Just balance your numbers, and that's all. So we end up usually changing to an element that's 2 less on there on the periodic table. So now we'll go through beta decay. So beta decay, there's 2 different types, positive and negative. Negative is the most common, but positive does happen once in a while, so we have to look at that too. And basically what happens is we're not removing neutrons and protons like we are with alpha decay, but what happens is in a beta negative decay is one neutron actually splits up into a proton and an electron. So the total masses, if we look at the total masses, remember a neutron was slightly bigger than a proton, and some of that difference is due to the electron sort of being added on. So some scientists think a neutron is basically just a proton and electron merged together, which so our charge neutralizes and our mass would end up being slightly bigger. So because it ends up being changed into a proton, we end up getting one more proton in the reaction, and then we get this extra electron that gets ejected, and it gets ejected as just like a regular electron, but because it wasn't original, it was conceived, we call it a beta particle, and we write that as -1, 0, beta. So the -1 takes care of the charge and the fact that we're gaining a proton, and then the 0 just means there are no protons or neutrons in that ejected electron. So the only, let's go back here. So we look at this example. So we just have calcium 46. So we have 4620 calcium, and we have -1, 0 beta. So all we have to do is add 1. So the 21 plus the -1 would give us the 20. So our new chemical ends up being 4621 SC. Okay. So there's one other slight thing that we got to be careful of. So when we have a decay type of equation, so if you look at this one, we had 46 calcium and it changed to 46 SC, which is so we get the 4621 scandium. So then we got to be careful of, if we worry about conservation of momentum, what ends up happening is that ejected electron ends up moving in one direction. So let's sort of picture our calcium being an original stationary element, and when it undergoes chemical reaction, it changes to scandium, and we get one electron being emitted. So using conservation of momentum, that means there had to be something going the other way to balance things up. So what they found out was there is a small particle that accounts for the mass difference, and that particle ends up being neutral, so they call it a neutrino. And in this case, we call it an antineutrino, and we're going to get to that a little bit later on, but we write it as, we just say that there's some sort of neutral particle that has a speed going in a certain direction, so we just write it as a v, velocity of some neutral object. We put a little slash over it to indicate that it's an antineutrino. So the neutron then goes from a neutron to a proton, an ejected electron plus this anti-neutrino. So the other type is beta positive decay. And in beta positive decay, basically the exact same process occurs, except it's the opposite signs. So we start with a proton, and it splits up into a positron, which is like an electron but positive, and a neutrino as well. So in terms of the chemical reaction, you basically do it exactly the same way, except your beta positive particle, you just write it as a 0 and plus 1, so when you do the math on it, you would subtract one number from your periodic table. So if we go through this example, we got potassium 40, so we'd write that as 40K19. And if we go through beta positive decay, so we get our beta with a 1, 0, so we know then the original, or the daughter element has to be 4018 argon. So the 18 plus 1 would add up to the 19, and then we write our neutrino, which is just a V. So the difference is, in beta positive decay, we get a neutrino being emitted, and in beta negative decay, we get an anti-neutrino, and the anti just means it's sort of like the opposite type of particle. And we're going to get into that in the next chapter, so you don't have to worry about it too much just yet. And our last type is gamma decay, and gamma decay is the exact same thing as we talked about earlier, but where it's just EMR radiation. So gamma was our highest frequency, highest energy of EMR radiation. So what happens is when we do alpha and beta decay questions or scenarios, kind of think of the nucleons, the protons and neutrons being all jumbled up, so they get sort of scrambled up, and some of them get emitted and changed and so on. So then during the process of getting those to be reformed into a nucleus again, a burst of energy is given off. So every time they get sort of rearranged, some of the mass gets lost and gets changed to energy. So the gamma radiation is that energy, and it's given off as a gamma wave or an EMR wave. And remember, it's high energy, so that means it'll pass through lead and other sources like that. And the math equation behind it is really easy. You just have to basically show the exact same thing and show the gamma wave. So we write the little symbol 4018 argon for this example. It stays as 4018 argon, but it just rearranges itself, and we get off this little gamma radiation symbol. So it's a really easy formula to work with. It's by far the simplest of the three, and quite often we don't worry about it too much because nothing really changes anyway. So the last thing we'll look at is sort of what happens if you have more than one. So a decay series, quite often you'll get a question where it just gets you to do several decays one after the other. So in this example, you can see we have 226 thorium. It undergoes alpha decay and it changes to 222 radium. And then it says that radium undergoes a beta negative decay, so it changes to actinium. And then that one undergoes another alpha, and then that result undergoes through alpha again. So if you get one of these questions, they usually just give you an original element, and it tells you to do an alpha, a beta, whatever, in each step to change it to. And obviously with any kind of radiation or emission, there's going to be some sort of risks. So here are some of the units you'll see: rads, grays, and sieverts. And they're just telling you how much energy could be absorbed by tissue. So a rad is 1 kilogram of tissue would only be absorbing 0.01 joules, so pretty minimal amount. A gray, about 100 times that much. And a sievert is way, way bigger. It's in the thousands or millions. So in a normal situation, a person can get about 0.5 millisieverts a year to be safe. Anything bigger than about 6 or so would kill you. And in terms of what you'd feel, so if you do undergo any kind of radiation exposure, the first type is radiation sickness. So that's usually where if you're getting cancer treatments and things like that, you're usually quite sick after because it kills some of your cells, plus it sort of ionizes some of them and causes you to feel like sort of sick, tired, flu-like symptoms. And if it's severe enough, obviously it would kill you later on. So in the nuclear bombs in Japan in World War II, the people that survived the initial blast usually died a few days later with the radiation sickness. And the second type is if you get enough radiation internally into your cells, it'll actually mess up your DNA a little bit, and the cells start growing a little bit differently. So basically what happens is you start modifying or changing the genetic structure, which usually leads to formation of some sort of cancer cells and so on. And that's about it. So we talked about the three types. We looked at how to do each of the three math formulas for them, and that's all.